Kirchhoff's voltage law states that in any closed-loop network, the total voltage around the loop is equal to the sum of all the voltage drops within the same loop. This can be represented in a number of ways, but is most commonly represented as sum of voltages equals 0, or source voltage E minus V1 minus V2 minus Vn is equal to 0. The polarity of each voltage load is important. Moving from positive to negative indicates a voltage drop, whilst moving from negative to positive will indicate a voltage rise. KVL works in both clockwise and anti-clockwise directions. For example, this circuit could be represented as E minus the voltages equals 0 as we move clockwise, or the sum of the voltages minus E is equal to 0 in an anti-clockwise direction. In this example, we are given two voltages and their polarities. If we work in a clockwise direction, we can solve this using E minus V1 minus V2 equals 0. Substituting our known values and simplifying gives us the answer of 5 volts. We can then use Ohm's law and other principles to solve for current with given resistance values. This is all simple for a series circuit. But what if we have a parallel circuit? For parallel circuits like the one on this slide, each individual branch is treated like a single closed loop with a voltage source. This can be represented by the sum of the voltages per branch being equal to 0. For the circuit in the image, the voltage across each resistor would be equal to the source voltage, as there is only one load to balance the equation. These rules apply for direct current, but what if we're using an alternating current circuit? KVL applies to both DC and AC circuits, however the calculations become more complex now as we are using complex numbers due to the sinusoidal nature. Alternating current is most commonly represented and most easily understood as a sine wave. The function of the sine wave can be represented by the function below. In this formula, D is the DC offset, A represents the amplitude, F is for frequency, and phi represents the phase angle or phase shift. If reading a graph, the frequency will need to be calculated using 1 over the period t. The sine wave has negative values. To implement KVL as the current changes, we just simply switch the signs in our chosen equation, as the polarities on our load momentarily change. At V equals 0, the voltages are all 0. To determine a comparable integer for AC voltage that can be compared to DC voltage, we must use RMS, or root mean square. To calculate this off of a sine wave, we can either use the peak-to-peak voltage or the amplitude of a single peak. Kirchhoff's voltage law is a simple way of identifying and calculating voltages in any circuit. It can be implemented for both parallel and series DC circuits, as well as AC circuits using methods such as RMS voltage. Thank you all for watching.